Together, we are going to build a stronger foundation for even greater achievement in the future. Today, we are privileged to have our esteemed speaker who will address a topic of profound importance. That's a novel, sustainable approach to carbonization, induced corrosion, addressing climate change, low carbon concrete. This is actually a hot topic. And you know that as engineers, we should always be at the forefront of finding solution to all pressing challenges. Climate change and its impact in the society demand urgent attention, and sustainable engineering practices are actually pivotal to shaping a better future. So the topic of today, from my understanding, delves into the intersection of material science and environmental stewardship, and exploring new innovations on how low carbon concrete can handle the dual challenges of corrosion and decarbonization. And I'm very sure that our guest speaker will bring his expertise to this discussion. And I encourage everyone to engage actively. And at the end of the session, we'll have a question and answer session. And please do ask questions. And there is definitely going to be some takeaways that is going to impact us and our community here in Saudi Arabia and beyond. So we couldn't have any luck in the person of the speaker today, which I strongly believe will do justice to the topic. Engineer Salim, you are welcome to this presentation, to this webinar. I know you are very busy at this time, especially now. I know it's evening in the UK. You must have been very busy today. So thank you very much for your presence. And so without much ado, I would like to call our technical secretary, Engineer Muiz, to read the citation of the speaker. Thank you very much.
All right, thank you very much, Mr. Chairman. So today we have with us a distinguished civil engineer, that's Engineer Salim Malami, who is currently at the tail end of his PhD at Heriot-Watt University in Edinburgh. He specializes in the sustainability and durability of reinforced concrete under climate change impacts. His research focuses on modeling the effects of carbonation and chloride-induced corrosion in sustainable concrete, integrating life cycle cost analysis and life cycle assessment to optimize cost and minimize CO2 emissions. So Engineer Malami has his master's degree from Near East University in Cyprus and his bachelor's degree from Bayero University, Kano. He also has a strong field experience as a civil project engineer in various organizations in Nigeria, as well as academic background at the Kano University of Science and Technology. So Engineer Malami is a committed advocate for sustainability. He's also a member of various professional organizations. He's a certified engineer by Coren, a member of American Society of Civil Engineers, an institution of civil engineers in the UK, as well as Nigerian Society of Engineers. So without further ado, we welcome Engineer Salim Malami to commence with his presentation. So you can share your slides, Engineer Salim.
Thank you very much. Can you see the screen?
Yes, it's up now.
Okay. Can you hear me?
Yes, I can hear you very clearly.
Okay. So thank you very
Maybe
much.
you can move it to presentation mode. I think you can put it in presentation mode.
Okay. So thank you very much for having me at this time. So as you know, my name is Salim Idris Malami from Heriot-Watt University doing my PhD here. So I'm here to present my topic, that is novel sustainable approach to carbonation induced corrosion addressing the climate change of carbon concrete, taking a reinforced concrete bridge in Lagos as a case study. So, concrete is the most popular construction material in the world, with annual uses of around 30 billion tons worldwide, which is terrible. Approximately each person in the world consumes 3.5 billion tons of concrete yearly. Me and you, we are consuming concrete every day because even if we are not eating it, we are now under shield, under concrete. Maybe the building that you are inside is made of concrete. That's why we say we are consuming concrete yearly by this amount. So 8% of the global carbon dioxide emission is contributed from concrete industries. That is by manufacturing Portland cement. That is Portland cement. That is cement that we use in concrete. This is happening during calcination. That is heating the limestone at high temperature, which is around 1600 to 1800 degrees Celsius, which produce high amount of carbon dioxide in the atmosphere. So we are always after net zero. We are always advocating about net zero, reducing the emission because of the effect of climate change in the world. So even here, like in UK, there are many agitators or advocates about this climate change. They are also like advocating to reduce the amount of concrete or to reduce the amount of cement in order to reduce the amount of carbon dioxide. Some even are calling to shift from using cement and concrete with to replace it with timber, that is wood, which is not possible because at this time, if you want to reduce the amount, that is 1/4 of the concrete that you are using in the world with timber, like you have to produce like 1.5 times, or to produce a forest with a size of 1.5 or 1.5 times of size of India, which is not possible. Just to replace 1/4 of the concrete used with timber, which is not possible. For you to understand what is the size of India, like the size of India is around 3.28 kilometers square, the size of India, which is for us to understand, like the size of Nigeria is like 923 square kilometer, like 900,000 900,023 around like that kilometer. This means India is like 3.6 times the size of Nigeria. So this is a huge. So you cannot replace concrete with timber or material like that. The best method that we are proposing is to replace cement from in concrete with supplementary cementitious material like GGBS, fly ash, and the new that is novel material that we call it LC3, that is limestone calcined clay. I'm now working with in this type of concrete also LC3. So we can replace it. We replace it in the cement. When you reduce the amount of cement in concrete, this means you reduce the amount of carbon dioxide in the atmosphere. Since you reduce something that is used to produce that amount of carbon dioxide in the atmosphere. But the problem we have, when you want to replace the cement in the concrete, you have to test it and see its sustainability. So, as you know, this cementitious material increase the rate of carbonation, which is lead to corrosion in reinforced concrete. So this means we have to test the sustainability and see. So what is this carbonation? We have to know what is this carbonation. This carbonation is the reaction between atmospheric carbon dioxide with calcium carbonate, one of the cement hydration product. We know in concrete there is when cement react with water, it produces some binding materials. We call it calcium hydroxide, which make it bind to improve the strength of the concrete. So this actually concrete is high alkaline in nature, with high alkalinity around like 13.5 to 14 in degree pH. So this means concrete is high alkaline in nature. This high alkalinity provides a protective layer. We call it passivation layer that protects the embedded reinforcement inside the concrete from corrosion. So when carbonation occurs, this layer that prevents the reinforcement from corrosion breaks, then the concrete becomes prone to carbonation. So this means We replace it, but there is a possibility of corrosion to occur. This corrosion or this carbonation obeys the Fick's law, which is obey the Fick's law. That is like x is equals to root of time. That is the depth of carbonation is equals to square root of time, and it follow with k constant, which is corrosion carbonation coefficient, which you use to determine the durability of the concrete. So in this study, what we do life cycle cost analysis and life cycle assessment in order to evaluate the long-term performance of the concrete, that is 100 years. So what you consider, we consider the complete cycle of the concrete, that is from starting of the concrete, taking the material, taking it to site, mixing the concrete, and building the structure. So we as we assess the amount of carbon dioxide that is produced during all these processes and the cost of material that will be used in the material. So in this, we use like probabilistic approach, because the reason of that, there is uncertainty, because this carbonation depend on like temperature, humidity, and the carbon dioxide scenario, that is the amount of carbon dioxide concentration within the area. So we consider like probabilistic approach in order to avoid all those errors, in order to eliminate those errors from uncertainties. So the study uses this method and select the type of concrete, that is PS, that is bridge from Lagos. We selected one of the, like I am from Nigeria, so I just take my case study to my own country, like that is Nigeria. So we take a concrete bridge because Lagos has all the possibilities. They have the temperature that is favorable to carbonation. They have the humidity that is favorable to this carbonation. So I take Lagos as a case study, because if you go to Lagos, you will see many different buildings that are made of concrete with corrosion, with spallings. This is happening most of the time because of corrosion, but we are because of carbonation, but we are not addressing it because Lagos is a city which is busy, many companies that are producing high amount of carbon dioxide, and there is humidity at the area, and their temperature are also feasible for this carbonation to occur. So that's why I take this Lagos as a case study. So we take a bridge, new bridge, with a piers. What is a pier? Pier, that is like a column. When you go to a building, there is what you call, we have different part of bridges. Maybe in the next slide, I will show you what it means by pier of a bridge. So the strength of the concrete we use is 400 megapascal with water binder ratio of 0.55. Then the concrete cover, we used 25 millimeters. Three types of concrete are considered in this. That is the concrete that is replaced with GGBS, that is ground granulated blast furnace slag, which is a waste material from iron producing companies, and also FA, fly ash, which is like waste from thermal power station. Then we consider concrete, which is 100% Portland cement. So the length of the piers or height of the piers is 4 meters, which has like which is a round or circular in shape with 0.6 diameters. With then we consider the amount of carbon dioxide that produced from the steel industries as 8.4. So these are the properties of the materials that we use in the probability calculations. So this is the exact picture of piers. This is a bridge. This is a model of a bridge. This is what we call pier. In real case, this is the pier of a bridge. So we take the column of a bridge, that is internal columns. So the amount of produced by cement is, each ton of cement produce 860 kilogram of carbon dioxide, which is high amount. But see, fly ash produces only 0.1, and GGBS produces 79.6. Then the producing reinforcement, that is the steel inside the concrete, produces 412 kilogram per tons. Then the aggregate, that is when we say aggregate, we are talking about gravels and sand, that is transportation and everything, and grinding it, it produces 2.6. So then the cost of the material that we use GBP, that is UK pound, that is Great Britain pound. So each cement per ton is 120 GBP. For fly ash is 60. For GGBS is 75. For aggregate is 25. All these are the values that we use. Then for environmental variables, we take the amount of the temperature of Lagos as 27.6 degrees Celsius. That's and relative humidity as 80%. Then the amount of carbon dioxide in the environment, we use 415 ppm. Then we use the discount rate, since we are using like probabilistic approach for 100 years. So we use discount rate as 2% of the cost from now to that time. So after we model, these are the results that we found. If you see, this is the result. So this is the graph that is showing the probability of service failure of the material. Like this, what we found that the concrete with GGBS starts the corrosion earlier, like just before 20 years, like 15 years, it started corrosion. See how it is started. And the concrete with like PC start its corrosion like after like 30 years or 35 years, while for FA started its corrosion around 40 years. So if you see from here, you will see concrete with like normal concrete with PC retain all the corrosion delay. But as time goes on, the corrosion, as what we consider two different times. We know in corrosion, we have what we call initiation period, and we have what we call propagation period. The initiation period is the time where the corrosion starts, while the propagation period is the time where when corrosion started, the time it takes for the concrete to fail. We call it propagation period. So if you see this graph, for GGBS, it started the corrosion, but the time in 100 years, the probability of corrosion is just 0.002. While for PC, the one that we are using, see, it delayed, but the probability of corrosion increases up to 0.006. This means it will deteriorate, or it is start cracking before that of GGBS and FA. So this is showing that this concrete that is with GGBS and FA is sustainable concrete. It can take time without corrosion. So that is for carbon dioxide emission. GGBS concrete is the most efficient option, with PC concrete being the worst, as we see from here. See the trend. The probability of starting corrosion of PC is higher than that of GGBS and FA. So predicted carbon dioxide emission and repair expenses are low, but secondary impact like carbon dioxide emission and traffic disruption during repair will be higher. But what we understand, there will be a problem with this, the time of repair. Like let's say we produce a bridge, so what you consider like the cost of like not the cost of expenses is the problem, but the cost that will disrupt, like that when during like repair of the bridge. So the delay that will cause, maybe there are shops that are close to the place, so you have to close the shop. Maybe you are just like it's a shop, maybe they are making like profit of 100 pounds in a year or in a week, sorry. But when you close the shop, you will lose that amount. So we are not after the cost of the material. We are after the cost that will of the disruption. That is the cost that you will lose during the repair of the material of the concrete bridge. Then GGBS concrete show the lowest durability against carbonation with faster failure of PS, that is corrosion initiation. As I have explained before, I say it will start corrosion earlier, but GGBS ladder resistivity result in lower corrosion rate and the propagation. The propagation of corrosion take longer time before it starts. So here is the table of the emission of each type of concrete. Like for PC, the carbon dioxide emission is around 469.39 kilogram and the cost is 249, while GGBS is 251.33 and cost is 237.6. For FA is 384.67 and for the cost is 2474. So if you see this, DDBS concrete has the lowest carbon dioxide emission and has the lowest cost. So this means is the most preferable concrete within these studies of ours. So conclusion. So this study demonstrates that using GreenConcrete significantly reduces the amount of carbon dioxide emission to the environment. And also, GGBS has a lower corrosion rate that is leading to more cracking in the concrete, that is leading to corrosion and failure of the bridge. GreenConcrete shows superior sustainability performance compared to standard Portland cement based on concrete anticipated climate scenario. Using the climate scenario that we use, that is the amount of carbon dioxide, the relative humidity and temperature in Lagos, it shows that GreenConcrete is more sustainable. It will take time, but it will take longer time than PC for the bridge to fail. So, and also there is a need to consider the propagation period. Then it shows us there is the propagation period for this type of GreenConcrete is higher. So this means we need some studies in order to know which type of concrete or how the propagation period occurs. So I think this is the brief explanation because I just do it brief. I know we have no time. So thank you very much.
Thank you so much, Engineer Salim. We really appreciate your time and the effort that you put to make the presentation. And hopefully many of the participants will have some questions so they can engage you directly with this. So please just raise your hand if you have any questions. All right, we have Engineer Maruf here. I think, Engineer, you can go ahead. And any other person can also raise their hand so we can take it one after the other.
Yeah, thank you, Engineer Malami, for that beautiful presentation. When it comes to corrosion, there are two phases to it. Some argue that the most critical one is the chloride-induced corrosion. And with what it appears you address CO2-based corrosion. And there are some other arguments that CO2-based corrosion always causes general corrosion, which is of less problem to RC members. What do you have to say to that?
Yeah, as you know, there are some research that I'm doing now on that chloride ingredient. So we know we have problems like here in Nigeria, we have some places that are producing large amount of carbon dioxide. So any problem is a problem. So we are trying to address this first. Then after then we go for that chloride ingredient. Even though most of the structures, especially like in Lagos, some of the structures I know they are inside the sea, which contain chloride, which like the percentage or that is the concentration has to be like if it has 0.1, the amount of the cement, it will start corrosion. It will break that passivation layer. So yeah, like chloride has more problem than this carbonation, but we have all the problems. So we have to address this one before you go to the other one. So I think this is maybe I answer your question.
All right. Engineer Maruf, any other questions?
Yes, even though I couldn't see the slide for some times. So maybe you have spoken on the next concern I want to raise, which is the one thing is material itself, which is I think GGBC blended concrete, from what I see in the conclusion. But are you looking into the direction of using, you have initiation time and propagation time?
Yeah.
And some other studies have revealed that if you have better cover, I mean the cover to the RC itself, if the CO2 gas ingress is delayed, it is more effective than even concentrate on the material itself. I'm trying to make some samples which vary the cover to the RC to determine the corrosion propagation time in your future studies.
Yeah, like in my studies now, I'm doing some research on different concrete. Some I'm doing on GGBS itself and using GGBS with limestone. and also doing FA and some FA with a limestone inside it, and also using LC3, that is limestone calcine clay, which is the novel concrete that is now trending, which is just like using clay to heat it some amount like half of that of normal cement to calcinate it, and use limestone and gypsum and add it. So what I'm saying, the most important things that I understand is the resistivity of the concrete. You understand? It is because this corrosion is just like iron, there's some particles or iron that are penetrating, especially like iron of chloride or iron of sulfate or anything. So it is resistivity, the higher resistance of the concrete is the thing that protect the ions like to penetrate within short period of time to reach the embedded reinforcement. So I think like now I'm testing the LC3. Like I've already the concrete is already inside the chamber. So I want to see the difference actually. Even though from the result that I found that the GGBS has more like resistance or high resistivity than that of fly ash.
All right. Engineer Maruf, is that all?
Yeah, thank you very much. Yes, it's okay.
Thank you so much. Before we go, we have Engineer Adeshina, but before Engineer Adeshina, I have one question here from Sophia.
Okay.
She says, what impact can modeling the concept have with regard to the study results? And also in Nigeria, what is the role of the corrosion significant? Or in what area is the role of corrosion significant?
So, as we say, in the modeling, we found that the sustainability of the concrete for 100 years to come, that is in the area that have carbon dioxide emission, and they have the environmental factors like temperature and humidity at that area. Like in Nigeria, as I said, Lagos, we have all these possibilities, and we have many platforms like, especially in Niger Delta area, or to say southwest in Nigeria, where there is exploration of crude oil. They produce high amount of carbon dioxide. They are sometimes even flying the gases to the atmosphere, and it is some of the platforms are inside the sea. So this means we have the problems. Even as I said, if you go to Lagos, you will see many buildings with spalling. That is the reinforcement is already exposed with corrosion on it. This occurs due to carbonation because Lagos area or some part of the southern Nigeria produce high amount of carbon dioxide. They produces it, and they have the humidity that is feasible to this, and they have the temperature that is high. Like here in UK, the temperature, the extreme temperature is 19 degrees Celsius sometimes, but like in Nigeria, there are some parts that is even higher. Some even like in the north, sometimes it reach like 40 degrees Celsius. Like now, they found some petroleum in Borno, is it Kolmani area? They found petroleum. They maybe start exploration. Too. They have the gases. They have the carbon dioxide. When they produce, if you want to explore exploration, that's during exploration on the petroleum, you have to produce high amount of carbon dioxide. And like in Borno area, we have like Lake Chad and everything that may produce that humidity that will be feasible for this to occur. So I think this is related to our own country or to Nigeria. I don't know whether I addressed the question or not.
Yeah, thank you so much, Engineer Salim. I think, Engineer Adeshina, you have the floor now. You can engage with the...
Yeah, thank you very much, Engineer Salim, for the excellent presentation. I need two clarifications. The first one is, where is the location of the site for this research? Then secondly, do you have fly ash and GGBC readily available in Lagos, or were they transported from a nearby state? Then the last question, from the presentation, the cost of fly ash produced concrete is higher than the GGBS. What could have been responsible for this? Thank you.
Yeah. The first, like in Lagos, the site, what you said, just like a modeling, because what the most important is not the site where the bridge is located. We take all the material. We have the materials. We take the environmental condition of Lagos. That is the temperature, humidity, and some scenarios of carbon dioxide emission. We use it. just like a modeling. It's not a bridge itself, but we use it when we want to produce it. You can produce this kind of model in Lagos. I hope you understand this. Then the second question, you say, do we have GGBS and fly ash in Lagos area? Yeah, because fly ash is a waste product from thermal power stations. That is a ash from thermal power station. So we have thermal power station in Lagos, and we have it in Safele. Many parts of the country, we have this type of power station in Nigeria. And GGBS, it is from the iron producing company. That is the waste from iron producing company, and we have it in Nigeria also. We have companies that produce iron. So this means we have the fly ash. For the cost, maybe it is because of the availability of the material. Even like here in UK, like they are discouraging using this because they are always moving out, because they are not using coal now. They are using gases, and even the fly ash, they are saying that in some years the fly ash will not be available in the world, because we are always moving toward net zero. So that's why now we are engaging ourselves using LC3, that is limestone calcined clay, because we are using clay to heat it. We have clay in abundance all over the world. Wherever you go, you can find clay. You can use it. So I think this is maybe I address your question. So I don't know whether you have another question.
Yeah, thank you.
Yeah. All right, we have Musa Adamu. Engineer Musa, I think you have the floor.
Okay, Sam, good day to all. The question I wanted to ask, I think Engineer Adeshina has answered, but the problem is with regards to the GGBS. Actually, I think Nigeria, we are having problem with GGBS, Engineer Salim, because in mostly the Ajakuta, that is where we can get the main GGBS. But the problem is the Ajakuta steel company is not working.
Functioning, yeah.
And for every supplementary cementitious material, the first thing is the availability. Because we are talking of concrete, we are saying 30 billion tons of concrete is produced. Yeah. So you should imagine the quantity of material that will be used, for example. This is the first. Then the second one is regarding the cost. Actually, I also wanted to ask, generally, GGBS is more expensive than fly ash, because fly ash is more readily available compared to GGBS. So I don't know whether in the case of the UK or Nigeria, the opposite is the case. But in general, if you have done, if you are working on fly ash and GGBS, you will find that fly ash is one of the most, the cheapest supplementary cementitious material. That is industrial-based supplementary cementitious material. So this is my two observations that I wanted to make.
I think for the fly ash and GGBS, like the reason why it is sometimes it may be expensive here in UK, because they are always moving away from thermal power stations. They are not burning coals now. That's why. So it will be expensive, because they are always discouraging using it. They don't have it available, but they have many companies that are producing like ions, and so it is the GGBS is more available here. That's why it is cheaper here than fly ash. So for about the fly ash and the material cost of material, that's why I'm saying we are working now on LC3. That is using clay, just to heat the clay to what you call the oxidation. That is heating it to remove the water in it and making it like a clinker, and use it and replace it in a cement. You can even replace like 50% of the cement with limestone, gypsum, and that calcined clay. So that's why. And the clay is all available in the world. Wherever you go in the world, you can find a clay that you can use. But it depends the type of clay, how much you are going to heat it. So I think that is.
Thank you so much. I think Dr. Charles, you have the floor.
Thank you very much, and good evening, everybody. Engineer, as a layman, and if I want to have my building last for 500 years,
yeah,
looking at the rates of collapse of buildings,
yeah,
which we are yet to understand the basic reasons and technical, we just gloss it over, quacks doing their business. But now you are going into nitty-gritties, trying to identify some elements, some factors to it. I think we now start paying attention to some other factors. Now, if I want to build my house to last for 500 years, I know it's funny, okay? What should I be worried about? Is it the CO2 ingress and ejection or reject, or humidity, or CO2, salt content of the soil, or the iron quality, because we now see the different kinds of quality of iron that is in the market. Some are resistant to maybe salt impacts and other factors that may be causing corrosion in the iron. What are those key factors that I should be worried about, and then what are the mitigations for average layman?
Okay, thank you very much. You know, as engineers, there are 13 things that you consider. There is factors that you consider in every engineering design or in every engineering aspect. The first is safety. Then we consider cost. Then we consider aesthetic. The first, you have to consider safety of the structure. Secondly, the cost. That is, you have to optimize, not the low cost or less cost. Optimize cost. Then we consider aesthetic. That is the beautification of the structure. So when you want to build a house, the first, you have to involve engineers, because they have to take the soil samples and use that soil samples to design the foundation of the structure, because the foundation is the one that is holding the whole structure. So we have to take the soil samples and see and check the bearing capacity of the soil. That is the amount of the load that soil or the foundation can take without causing any problem, with a minimum like consolidation or something like that, what you call it. So then secondly, after that, then you check the materials. After we design it, then you check the material, the type of the material, the quality of the material. This involves this road itself. That is reinforcement. We call it reinforcement in civil engineering. So after reinforcement, the strength of the material, then you check the aggregate itself. Then even the cement type that you can use. After this, then you take good engineer or someone that will make sure the person that will build the building follow the instruction or the code that is given by the designer. That's what you have to consider, because what you found that the material that you build there, like when we are talking about carbonation, sometimes what prevent this carbonation is like the material that you use. After the material that you use, then the type of cover that covered the reinforcement. So I think when you want to build a house, these are the things that you have to consider. First, as I said, you call an engineer, take the soil sample, design it, know the bearing capacity of this. After you know the bearing capacity of the soil, design the foundation itself and all the structural part. When I say foundation, I just stop at foundation, but we have different parts of the building. Like we have after foundation, we have beams, columns. After columns, we go to beams. After beams, we have slab. So these are the components of the structure of civil structures. So after design it, you check the material, you buy good materials, then you hire an engineer that will be a consultant to the building, so that you maintain the specification by the designer. So I think this is what you have to consider when you want to build a house as a layman.
Thank you.
Thank you so much, Engineer Charles and Engineer Salim. We have one question here in the chat. The user says that, what can be the effect of such research in freshwater environment? So he wants to know about freshwater environment. What's the relevance of the research in freshwater environment?
So the effect of the research in freshwater environment, can I call it freshwater environment? Yeah, we are talking about gases. Even there is no water in the place, the building must not be inside the water. It may be outside the water. Maybe even in the coastal area, there are some places that the building is not inside the sea. But if there is a gases that can be produced and can penetrate inside the concrete, can cause the effect of carbonation. So we are not talking about the fresh water. The problem of fresh water, when we are talking about fresh water or salt water, it is about ingression, chloride ingression, not carbon dioxide. You understand? The carbon dioxide effect is on building itself, not inside the water. So wherever you are, if there is humidity, there is a carbon dioxide, and there is temperature that is feasible to carbonation, it may occur on that concrete.
All right, thank you so much, Engineer Salim. I think so far so good. I don't think we have any more questions. Does anyone have one more question? Otherwise, we moved on to the next item on the agenda.
Engineer Muiz, check the chat box.